Hello and welcome to week 9. This is the beginning of the second week covering the exciting topic of image and video compression. Image and video compression represents one of the major topics in image and video processing. Compression is one of the enabling technologies behind the multimedia revolution we are experiencing. Last week we talked about lossless compression, and this week we'll see how it is used in lossy compression. As I mentioned last week, what distinguishes lossy and lossless compression is not the exploitation of the correlation in the data, since it's shared by both approaches, but the removal of the perceptually relevant information. This is done through quantization. This is the topic of this week's first two segments. It's actually re-quantization since the data is already in digital form. We will then cover predictive coding, more specifically DPCM, fractal encoding, transform encoding, and also the well-known image compression standard JPEG, and subband encoding. We will see that each and every image and video lossy compression system consists of three building blocks. The first one to perform redundancy removal, followed by one to reduce entropy, and finally one to perform entropy encoding. What therefore differentiates lossy and lossless compression is the middle block, while what differentiates the various lossy compression techniques we just mentioned above is the first block of redundancy removal via prediction or self-similarity or decorrelation, while the other two blocks remain the same. We will cover both scalar and vector quantization. Both techniques are part of any lossy compression system, or they can be implemented on their own right as compression techniques. In this first segment, we'll discuss scalar quantization. We'll discuss uniform quantizers, but also a PDF-optimized non-uniform quantizer, also referred to as the Max-Lloyd quantizer. We will also talk about the principle of compounding, based on which a non-uniform quantizer is implemented utilizing a uniform quantizer. So, let us start with this exciting topic. Any lossy data compression system, be it a speech, audio, still image, or video compression system, and we'll be studying the last two during this and next week, consists of the three building blocks shown here. According to the first one, the redundancy in the data is removed. As we mentioned earlier, the existence of redundancy in the data is one of the two reasons data is compressible. The second building block is the reduction of the entropy of the data. The reason we want to take this step is that according to the Shannon coding theorem we covered last week, the smaller the entropy of a source, the fewer the number of bits we need to encode such a source. This is the step that reduces the bit rate in representing the symbols of the source. The final building block is the further reduction of the bits in representing the source symbols by using a lossless coding scheme, which ideally will achieve entropy. More specifically, two important mechanisms to remove redundancy is prediction and transformation. We talked about linear prediction last week. The main idea is to utilize the correlation in the data in performing prediction of a pixel based on the values of its either spatial or temporal or spatiotemporal neighbors. The idea behind the use of a transformation is to decorrelate the data. Then it's easier to tell which transfer coefficients are more important than others, and in the next step try to keep the important ones in pristine shape while discarding or heavily quantizing the less important ones. Entropy reduction is achieved through quantization, the process that turns the continuous values of a discrete signal into discrete values, or re-quantization when discrete values are further restricted into a smaller set of discrete values. In designing such quantizers, the properties of the visual system are taken into account so as to remove the perceptually relevant information, the second reason we mentioned earlier for the data being compressible. Finally, in performing lossless encoding of the either quantized prediction error or the transfer coefficients, any of the lossless techniques we covered during last week, such as Huffman, LZW, and arithmetic coding and their variants, can be utilized. This center block of quantization distinguishes lossless and loss encoding. In other words, if it's not present, the system is lossless. Like, for example, lossless JPEG that we covered last week. With that, if you recall, a predictor was used out of a set of predictors for redundancy removal and arithmetic coding for the lossless representation of the source symbols representing prediction errors. We will cover quantization in this lecture. It's an irreversible process and contributes the most towards the reduction of the bitrate. So in summary, any lossy compression scheme we will cover in these 2 weeks, and any other one that is not covered in this class consists of these 3 building blocks shown here. This week we are going to cover the following topics. We will talk about quantization, both scalar and vector. We will then describe some approaches, which I call basic approaches, such as subsampling and pulse code modulation. We will revisit differential or predictive encoding, and more specifically, we'll derive the expressions for differential PCM. We will talk about fractal encoding, a very interesting approach in its own right. Continue with transform coding and its application to the well-known standard of JPEG. And finally, we will discuss subband coding. There are other topics that we will not have time to cover here, such as wavelet-based coding, which relates to subband coding. So how does a quantizer look like? Here is an 8-level uniform mid-rise quantizer. It's a mid-rise because it rises here in the middle, as opposed to a mid-stop or one with a dead zone. On the horizontal axis, you see the input intensity values of an image or the amplitude values of a signal in general. They can be continuous numbers or discrete numbers. According to the mapping defined by this function, all the input values, say between delta and 2 delta, are mapped into this value 3 delta over 2. If these input values are continuous, then we have infinitely many values between delta and 2 delta that are all mapped into this one value 3 delta over 2. If on the other hand they're discrete, then a finite number of them are mapped into this one value. So for example, if delta equals 10, then the values here between 10 and 19, we close the interval on this side and keep it open on this side, are all mapped into this value, which is going to be equal to 15. It's clearly an irreversible process. If we know the number 15, we cannot tell which of the 10 values in this 10 to the 19 range was quantized to the value 15. It is a uniform quantizer because the steps, these are the steps, except of this one at the end here and here, are all the same. They have exactly the same value. And the output has only 8 discrete values, the quantization levels. So to define this quantizer, we need to know the decision boundaries. These are the decision boundaries, as well as the quantization levels. Of course, in this case that we have a uniform quantizer, as far as the decision boundaries goes, all we need to know is the step of the quantizer denoted by delta. And clearly, if the range of values of the input is finite, let's say between minus 255 to 255, then we can make all these steps exactly equal. Here is another view of the uniform quantizer. The quantization levels here are denoted by R of I, and the decision boundaries are shown here. They're typically closed on one side and open on the other. So the interpretation is that all the values inside this interval here are mapped to R of I. Now, suppose we know the distribution of the intensity values of the input image by computing, for example, the histogram of the image. So assume that this distribution looks like this. So we have many more values concentrated in this region than in these regions over here. When we design a quantizer, we fix the number of quantization levels, and we want the error we are incurring, the quantization error, to be as small as possible. So then how shall we design a quantizer in this case? Shall we make the quantizer step sizes the same as before? Shall we design, in other words, a uniform quantizer? Or can we do better than this? What does our intuition tell us about it? If we think for a second, we have many more values around here than in these regions. And we would like for these values the quantization error to be as small as possible. Since we have many of them and the overall quantization error is the sum of the quantization errors per region in the quantizer, or per bin as it is called, for the values that are in here, again, we want a small quantization error, while with the values that are out here, we can allow larger quantization errors. Now, how can we have a small quantization error? We can do that by using a smaller step size, or in other words, by doing finer quantization here in the middle, where most of the values are concentrated, and doing coarser quantization, larger step sizes in the regions out here. Our intuition is actually correct, because as we'll see, the quantizer that gives us the smallest quantization error is a non-uniform quantizer, as shown here. Again, small quantization step sizes here in the center, and larger step sizes in the regions where this probability density function or histogram has small values. And this can be mathematically derived, as we'll show right away, and again, it confirms our intuition. But first, let's define the quantization problem a bit more rigorously. Here's a definition of the quantizer Q of x. X is the input to the quantizer, a continuous number representing the amplitude or intensity value of a sample or a pixel. According to it, the values of x between b I minus 1 and b of I, the decision boundaries, are represented by the quantized or reconstruction level y of I. Assume we want to design an m-level quantizer. The variance of the quantization error is equal to this. Inside two consecutive boundaries, b I minus 1 and b of I, which are referred to as a bin, bin, the variance of the error is equal to the error squared. X, all the values x are represented by y of I, so this is the error squared, times the probability density function of the random variable x. This is just the definition of the variance. Since I have m levels for the quantizer, or m bins, the variance of the total quantization error is the sum of the individual bin error variances, since the quantization per bin is done independently. In the quantization process, we are interested in counting bits, or in other words, in encoding the quantization levels y of I. These are the symbols of the source, a problem we covered last week. The bit rate associated with this quantizer is given by this expression. So L of I is the length of the code word which is used to encode the level y of I, and this is multiplied with the area under the probability density function curve inside this bin, from b I minus 1 to b of I. So this is summed over all bins here m, and therefore it gives us the average cold wear length. So formally, the optimal quantizer results from the minimization of the variance of the quantization error with respect to the decision boundaries, the reconstruction levels, as well as the binary codes, subject to a rate constraint. Or we can deal with the dual problem, which is the dual formulation, which is the minimization of the rate with respect to decision boundaries, reconstruction levels, and binary codes, subject to a constraint on the allowable quantization error. We show here again a scalar quantizer with f representing the input signal with continuous amplitude values or intensity values, and r of I representing the reconstruction levels, while d of I, I minus 1, d of I are the decision boundaries. We will derive next the solution of the optimal quantizer, assuming that fixed codes are used to represent the reconstruction levels. In other words, we are not optimizing over the bit rate for representing the quantization or reconstruction levels. We are solving, therefore, a simplified version of the general problem we described in the previous slide. The problem now is unconstrained. So, assuming that we use fixed codes to represent the reconstruction levels, we want to design an L-level quantizer. So in other words, we want to find the d of i's and r of i's so that the variance of the quantization error is minimized. So this is the statement of the design problem of the optimal quantizer. Here is the expression of the variance of the quantization error. P of f is the probability density function of the input intensities, and again we have L bins or L levels, and this is an expression we saw earlier. We want to find the minimum of this expression. There's no constraint again now since we use fixed codes to represent the reconstruction levels. The necessary conditions for obtaining a minimum are that the partial derivative of this variance of the quantization error with respect to the reconstruction levels r of k is equal to 0, and we have capital L such reconstruction levels. And also the partial derivatives with respect to the decision boundaries are also equal to 0. We have L plus 1 decision boundaries. However, the first and last decision boundaries are known, and therefore we only have L minus 1 unknowns. We will find next what these partial derivatives are equal to. Let us first look at the partial derivative of the variance of the quantization error with respect to the reconstruction level r of k. If we look at the expression of d, it's the sum of those integrals. R of k appears only in this integral from dk minus 1 to d of k, because when f is inside this interval, then all these values are mapped to r of k. The differentiation operation comes inside the integral, and then I have r of k minus f squared, so the derivative is 2 times the term r of k minus f times the derivative of r of k minus f, which is equal to 1, and therefore I end up with this expression. So now if I split the integral into 2, that's how this form looks like. R of k clearly is a constant with respect to the integration, which is done with respect to d of f, and therefore if I solve for r of k, I end up with this expression. What this expression is telling me is that the reconstruction level is the centroid of the probability mass in this quantization interval. We want now to evaluate the partial derivative of the variance of the quantization error with respect to the decision boundaries. Things become a bit more complicated simply because the decision boundaries appear as the limits of integration. We need therefore a formula to let us know how to carry out this differentiation, and this formula is due to Leibniz. So the derivative with respect to a of this expression here equals the integral here of the partial derivative of the integrand with respect to a plus the integrand evaluated at the upper limit of integration times the derivative of the upper limit with respect to a minus the integrand evaluated at the lower limit of integration times the derivative of the lower limit. We will apply this formula to find again the partial of the variance of the quantization error that I showed a few slides earlier. If we look at that formula, we see that there are two terms that depend on d of k. This first one where d of k is the upper limit of integration, and the next one where d of k is the lower limit of integration. For values of f between d of k minus 1 and d of k, they are all mapped or quantized into r of k, while when f is between d of k and dk plus 1, all the values of f are quantized into r of k plus 1. If we apply Leibniz formula to carrying out the partial of these two terms, what we obtain is this. Let's walk through the first partial derivative here. Here is the integrand. If I take the derivative of this, the partial with respect to d of k is equal to 0, since it does not depend on d of k. So this first term is going to be 0. Then I have the integrand evaluated at d of k. So instead of f here, I'll put d of k. Instead of f here, I will put d of k times the derivative of d of k with respect to d of k, right? It's a bit of an unfortunate notation here, too many d's you might say, minus the integrand evaluated at dk minus 1 times the derivative of dk minus 1 with respect to d of k, which is equal to 0. So the derivative of the first term gives rise to just one term here, and similarly the derivative of the second term will give rise to this second term. And you can walk through the steps here in a rather straightforward way. We see that p of d of k is a common factor, it's constant, and clearly these derivatives are equal to 1, and therefore what I'm left with is this expression here. If I apply the identity a minus b squared equals a minus b times a plus b, then what I obtain is this expression. D of k is cancelled out, therefore this is a constant, does not depend on d of k, and from the second term I obtain that d of k equals to this, and this is just the midpoint of two neighboring reconstruction levels. We see now that if the intensities of the input image follow a uniform distribution, or in other words, p of f is a constant, then if we use the formula that gives us the reconstruction levels, it's very straightforward to see that r of k is the midpoint of the two consecutive decision levels. And since we have that for any distribution d of k is the midpoint of the reconstruction levels, we see that in this case the resulting quantizer is a uniform quantizer. So this is an interesting result, that the optimal quantizer when the PDF is uniform is the uniform quantizer. Uniform quantizers are used widely because they're very easy and straightforward to use. When we covered enhancement, we called an image that has a uniform PDF of intensities an image with equalized histogram, and therefore when we do quantization, if we are given an image and we perform histogram equalization, then we know that the uniform quantizer we can apply to such an image is the best possible one in terms of minimizing the variance of the quantization error. So here is another potential use of the histogram equalization technique that we covered when we talked about image enhancement. If we were to apply a uniform quantizer in quantizing sources with different distributions, we can obtain the optimum step size by minimizing the variance of the quantization error with respect to delta, the quantizer step size. So the steps are shown here in this table for different alphabet sizes. That is when the number of quantization levels are equal to 2, 4, 8, and 16. The signal-to-noise ratio is shown as well for all these three distributions. For a uniform distribution of amplitudes, a closed-form expression can be obtained for the SNR in terms of the quantization level. More specifically, the SNR equals 6.02 n, where n is the number of bits to represent the quantization level. So here I have m equals 2 to the first equals 2 squared equals 2 to the fourth. So we see that for n here equal 1, I have 6 dB. For n equal 2, I have 2 times 6, n equals 3, n equals 4. For the SNRs, for the Gaussian and Laplacian distributions, they are obtained based on experiments. We see that the best performance is achieved when a uniform quantizer is used for the uniform distribution of the input data, because, as we saw a few slides earlier, this is the optimal quantizer. We show in this table the values of the decision boundaries, d of I, and reconstruction levels, r of I, for two different distributions of the input data, Gaussian and Laplacian, as a function of the number of reconstruction levels, 4, 6, 8. These results were obtained by using iteratively the two relationships for the optimal Max-Lloyd quantizer that we derived a few slides ago. The distributions that have heavier tails, that is the Laplacian, have larger outer step sizes. If you compare this step size to this one is larger, while these same quantizers have smaller inner step sizes. So this one is smaller than this because they're more heavily picked. The SNR values are also shown. Comparing these SNR values to the table in the previous slide where the PDF optimized uniform quantizers were shown, we see that these SNR values here are considerably improved. This is to be expected because these are the optimal quantizers for these two distributions, while the uniform quantizer was not optimal for the Gaussian and the Laplacian, while was optimal for the uniform distribution. We show here the effects of uniform quantization on this 8 bits per pixel original image. When a 1 bit per pixel quantizer is used, here is the resulting image. This particular quantizer has this shape. The input values range from 0 to 255, since again it's an 8 bit per pixel image. And then the values between 0 and 127 are mapped onto the midpoint of this region, which is equal to 64, while the values from 128 to 255 are mapped into the midpoint of this region, which is equal to 196. When 2 bits per pixel are used, here is the resulting quantized image. 3 bits per pixel and 4 bits per pixel are shown here. Clearly, in this case, we see these artificial contouring effects. They're not as visible when 3 bits per pixel are used, while for this 4 bits per pixel image, it looks quite similar to the original one. Therefore, this uniform requantization is a simple, naive maybe, means to achieve compression. In this last case, the compression factor is equal to 2, since we go from 8 bits per pixel to 4 bits per pixel. VCDemo, the program I discussed earlier in the course, was used in generating these results. We saw when we derived the optimal quantizer that the step size is small. We are performing fine quantization in the regions where the input lies with high probability. In other words, the probability density function has large values. Instead of doing this, we can make the interval where the input lies with high probability large. This is the idea behind compounded quantization, as shown in the block diagram here. The idea of the compressor is to stretch the high probability regions close to the origin and correspondingly compress the low probability regions away from the origin. So this region here is stretched, while this region here is compressed. Therefore, regions close to the origin in the input of the compressor occupy a greater fraction of the total region covered by the compressor. The output of the compressor is quantized using a uniform quantizer, and the quantized value is transformed with the use of an expander. So the overall effect is the same as using a non-uniform quantizer. We clearly encountered these compressor-expander mappings when we covered image enhancement. Two compounding characteristics that are widely used today are the so-called mu-law compounding and A-law compounding. The compressor and expander functions have specific forms in these cases. The mu-law is used in North America and Japan, and the rest of the world is using the A-law characteristics.